Hello, everyone. We will wait a few more minutes after the hour before we get started, just to let some other people join. Good afternoon, everyone. Happy Friday. We'll go ahead and get started with some opening comments and some housekeeping items while we wait for everyone else to join. But yeah, thank you all for joining today's session. Just a quick introduction for those that I haven't interacted with previously. My name is Nikki Kazahaya. I'm one of the community managers here at SafeGraph. This is actually our first event of a new line of programming that we're hosting at SafeGraph called the Knowledge Series. Excited to kick it off with a session from one of our own here at SafeGraph, Eugene, who will be our guest speaker today. So since it is our first event, please feel free to provide any feedback. We're always looking to improve our programming for future events. So comments or suggestions are always appreciated. So see a lot of familiar names from the SafeGraph community in this session. However, if you're not already in the community or you'd like to invite your peers and colleagues, I will post a link in the chat to join. It's a free Slack community for data enthusiasts. You get access to our support team. You're able to share your work and just network with others in the GIS community. So I'm going to put that in the chat. A few other housekeeping items before we start. So we do have another event coming up next week, a week from today, the 16th, 11 a Pacific, 2 p Eastern. We'll be doing a fireside chat with Dr. Nicholas Christakis. If you weren't able to make it to our last one, it's basically a 20 to 30 minute Q&A, ask me anything session. So not every day you get to sit down with Dr. Christakis. So certainly encourage everyone to join. If you're able to make it out, I will also post this in the chat. So we want this session to be engaging as possible and make sure that everyone, regardless of their background on this topic, leaves with some valuable insights from this session. So if you've attended our previous events, you will know that we usually do 15 minutes of presentation, followed up by a 15-minute Q&A. So I think that might be a little bit too mechanical or sterile for this type of conversation. So we'll shake it up a little bit. So instead, as you think of questions, feel free to raise your hand or indicate in the chat that you have a question, and I will interrupt Eugene. And if you feel comfortable, I'll have you turn on your audio and video and have you ask the question live. So I do have one other question that I will put in the chat just to help us kind of steer the conversation. So my question to everyone is, what is your background or your familiarity with spatial data or GIS? So let me put this in here. So if you could just respond based on the number corresponding to your answer, 1 being not at all familiar, 5 being extremely familiar, that'll kind of help us gauge the conversation. So I will let everyone answer while I introduce our speaker today. So Eugene is an analyst here on the product team here at SafeGraph, whose work has been focused primarily on SafeGraph's patterns foot traffic dataset. Prior to joining SafeGraph, he completed his master's in city planning and urban spatial analytics at UPenn. He loves baseball, frisbee, and maps, and will gladly stay late to talk with you about any of those three. So at this point, I will pass it off to Eugene. Like I said, feel free to just ping me or raise your hand whenever questions come in, but I will pass it off to you.
All right, thank you, Nikki. Can you just nod if you can see my screen right now? Cool. All right, hello everyone, happy Friday. Thanks very much for joining today, and thank you to Nikki for the introduction. Today I'll be giving, I see there's already a chat. Nice, okay. Today I'll be giving a brief, maybe like 15-ish minute introduction to spatial data and GIS 101. The target audience for this discussion is someone who has some experience with and is comfortable doing programmatic data analysis with non-spatial data and is interested in starting to work with spatial data sets, whether they come from SafeGraph or some other place. As Nikki said, we'd like this to be as interactive as possible. It's a pretty small group here, so please enter any questions you might have in the chat as they come up. I'm monitoring it, Nikki's definitely monitoring it, and feel free to unmute yourself if you can, or raise your hand and interrupt me at any time. So a quick agenda for today. What is spatial data? Why spatial data? What's different about it, and why is it useful? What is GIS in quotes? What are some of the tools or file formats or workflows you'll encounter when doing quote GIS work? Then I'll touch on 2 important examples of the many bits of jargon you'll encounter when entering the world of spatial analysis. And then lastly, I'll leave you with some references and readings, and end with any questions that you might have. So what is spatial data? Spatial data is very simple. It's data with a spatial component. That's to say something like coordinates, a geometry or footprint, an address, or perhaps even just a state or a zip code. But you can categorize it and describe it in many different ways. SafeGraph's data, for instance, is geospatial in that it relates to places on Earth. It's about the built environment in that it pertains to human-made places. And it's data on human geography, which is to say it's data on people's relationships and interactions with their communities, economies, cultures, and institutions. And these are all centered around our concepts of place and space. I'm sure you could describe our data in many more ways, and that, of course, is just a limited subset of all the spatial data that's out there. In the course of your own work, you may have worked with or encountered spatial data in the realms of transportation, economic development, land use, ecology, weather, or even sports analytics. All that said, you can broadly think of spatial data falling into 2 categories: vector data and raster data. Vector data consists of points, lines, and polygons on a map. A bus stop is a discrete, precise point on a map. A sewer pipe is a discrete line on a map. And a building footprint is a discrete polygon. These data points are presented as precise shapes on a map, and they're best suited for things that have precise shapes and locations in real life. For instance, the building footprints in SafeGraph's data are vector polygons. A building is a discrete object on Earth, so it makes sense for us to represent building footprints as precise shapes on Earth, even though we probably don't get them right down to the inch or whatever unit measurement you might be thinking of. This is in contrast to raster data. Raster data is a grid of uniform cells or pixels that each contain some sort of value. These inherently represent geographic estimates. One example is a temperature weather map. You can't really draw temperature precisely because that requires you to know the temperature at every infinitesimal location in the area that you're mapping. So instead, we draw an estimate. We can draw grid cells that are perhaps something like 1 square mile each, and then we can report the temperature from somewhere inside that square mile. And that's largely how like the weather maps you see on television work. They're not showing you it's 86 degrees at every single point between here and New York. They're saying it's roughly 86 degrees somewhere between here and New York. So one reason that you might use raster data is because the phenomenon itself, like temperature, doesn't really make sense to think about using precise shapes the same way that it did for like the building footprints we were discussing. Another reason is that it might save you memory or computational resources. If you want to map the location, say, of something like every single car in the US, you could perhaps get the coordinate for every single car and then map it and then try to print it out or just show it on the screen. But it'd be a lot of data and it's going to be really hard to work with and very expensive to process. So instead, maybe you could do something like draw another grid of 1 square mile cells or 10 square mile cells across the US and just count the number of cars that's in each cell. And depending on your use case, that visual might be enough, that estimate might be precise enough, and it'll save you a lot of computation down the road. In the case of SafeGraph, SafeGraph's data is all vector data. We use points when we give our coordinates for our POI centroids, and we use polygons when we talk about building footprints or geometries. But we do use some raster data in the production process. So for instance, we employ some amount of object detection from satellite imagery, and those satellite images are examples of raster data. So I'd like to move on to discussing sort of why spatial data, what makes spatial data useful, what makes it powerful. One reason is that it's super easy, really easy to visualize. People love maps, and they can understand them much more personally and viscerally than perhaps a scatter plot or a bar chart that's expressing actually the same information. The problem with maps is that it's very easy for them to be misleading. A fundamental challenge in spatial analysis and visualization is the modifiable aerial unit problem. Basically, you can slice up and aggregate spatial data in an arbitrary way that tells a different story. And this is basically the same problem you encounter when you're doing something like choosing the bin size when you're drawing a histogram. So in the top right corner, you see a bunch of points, and they're evenly spaced. And if you aggregate them into evenly sized square grids, you also get an even allocation of points. But if you draw a bunch of arbitrary shapes, and maybe these are things like states or congressional districts or counties or whatever, you get the sense that the population is actually not evenly distributed, even though when looking at the points, it obviously is. That's just visualization, but one application of the modifiable aerial unit problem with practical implications is gerrymandering. You can split up and group populations in a way such that the minority population is the dominant population in the majority of groups. Similarly, the concept that you might be mapping won't necessarily align with the underlying geometries. So for instance, in the bottom left corner, if we look at a political map of US congressional districts, that map's going to immediately suggest to you that the country is a large majority Republican. But a cartogram, which sizes states based on their actual electoral vote allocations, will tell a much more balanced story. And it comes at the cost of distorting the real shape of the country. So these are types of trade-offs you need to consider when you're visualizing spatial data. Secondly, location can also serve as a useful, like, quote, join key or grouping variable. And what I mean by that is that if you know two POIs are in the same county or city or neighborhood or just some distance apart that you consider close, you can then make some reasonable assumptions about them. Their customer base might have roughly similar demographics, or they experience similar average daily temperatures, or they have to navigate the same municipal tax code, etc. This is not dissimilar from a similar inference you might make using time periods. For instance, if you don't know anything about two groups of people, except perhaps the decades in which they were born, you could join people together based on that decade, and you can make some reasonable assumptions about them, like maybe their income level or their music tastes, things like that.
So Eugene, I'm going to interrupt you just for a second. So when you mentioned two POIs being in the same place key hexagon, so I find that kind of comes up in a lot of my conversations with our initial onboarding members. Can you explain exactly what you mean by place key hex?
Yeah, so a place key hexagon is there's a grid system called H3 that was created by Uber. It's a hierarchical grid system, and you can see it pictured here. Basically, they covered the entire world in a series of hexagons, and they're nested within each other. And place key, which is SafeGraph's attempt to create a universal join key for all physical places, is based off the H3 grid system. So the way place key works is there will be an encoding that'll say what the address is. So that'll be the first three numbers in it. And it might just be 222, and that represents an address within a place key. Then there will be a POI encoding that tells you what that thing is. So it might be that it's a bodega. So it'll be at address 222, there is -111, which might be a bodega. And then it'll say an @ sign, and then it'll give you a 9-digit encoding for the particular hexagonal cell on the Earth in which that bodega is located. So the idea here is that rather than trying to munge all the different types of address systems around the world and also dealing with all the typos, like I live in Philadelphia and people for some reason forget to put the H in Philadelphia all the time. It's very funny, but it's also kind of hard to work with. We can instead try to roll them up into something like a place key hex, which is roughly 4 acres in size. And we can say, listen, like we might not have resolved it necessarily perfectly down to the address level, but at least we can say these two things are probably located within this same 4-acre hexagonal cell.
Gotcha.
So on the note of, I guess, generalizable join keys or grouping variables, spatial data provides a whole new dimension on which you can model behavior. At the core of spatial statistics and modeling is a concept that the geographer Walter Tobler coined as the first law of geography. Everything's related, but closer things are more related. So this gets to the notion of spatial autocorrelation. How is measurement in some area dependent on measurements in nearby areas? Let's think about average income in a city. Do you think that wealthy people in a city tend to be positively spatially autocorrelated or clustered, negatively spatially autocorrelated or dispersed, or not spatially autocorrelated at all, so randomly located throughout the city? Of course, the answer here is that they're clustered, because we know that rich and poor neighborhoods exist. But what about something like new Amazon warehouses? Will Amazon cluster them or disperse them? You can also build spatial components on top of existing analytical frameworks. So for instance, Hotelling's law is an economic principle that states that it's often rational for competitors to make their products as similar as possible. Basically, they converge to the middle. And you can think about political candidates as they get closer to election day. They often end up converging on the centrist position. Well, you can apply that sort of framework to something like ice cream vendors on a beach. Why do they tend to cluster in the middle when it'd be far better for everyone involved if they stuck to their own territories? Because they know that no matter how close they get to each other, people on their side of the beach will go to them, no matter how far they have to walk within reason. And maybe they can also cut into their competitors' market share at the same time. This is a very simplified example, but we see it all the time with things like car dealerships and fast food. Why are competitors always so close to each other? Well, if you're somebody like Blackstone, which is the country's biggest landlord, you probably have a view on where companies site their locations based on their existing locations, the locations of their competitors, and geographic features like nearby roadways. And you can use that model to prioritize real estate acquisitions accordingly. So switching gears now, let's talk a little bit about GIS. What is this term GIS? Very simply, GIS is a geographic information system, and it's a tool for creating, visualizing, and analyzing geospatial data. I'll give some quick examples of these tools in the next slide, but one popular one you can see here is QGIS, which is a free open source desktop tool for working with spatial data. There are tons of GIS tools out there. Some are the desktop point and click variety, like Esri ArcMap or QGIS. Others are spatial extensions of existing popular programming languages like Python or R. And then there are spatial extensions of database technologies, which allow you to store and query spatial data efficiently. An example of this would be the PostGIS extension of PostgreSQL. And then lastly, there are web-based tools like Carto and Mapbox.
So, obviously in this page, you have a lot of different tools. So I'm curious to hear what's kind of like your toolbox as far as tools look like, and then like why do you decide to use some of those tools, and then maybe why would others prefer not to use some of those tools that you use?
Yeah, personally, like if I'm like just checking out a data set and it's like not a huge data set, I'm just kind of having fun with it, I'll usually load it into memory on my computer in R or Python and then work with the spatial packages there because they're super easy. They make it super easy to manipulate the data and visualize the data at the same time. In a more production setting, like in my day-to-day at work, I end up using things like Apache Sedona, which are spatial extensions on Spark, which can be a little more challenging to work with just because the data sets involved are pretty massive and visualization can be more challenging, but it is much more efficient than trying to load the data into pieces in memory in something like R or Python.
Gotcha, makes sense.
And then here, I'll go over a perhaps general GIS workflow for someone to follow when they're evaluating or analyzing new geospatial data. So the first step, of course, is you want to ingest the data, which is simple enough, but sometimes it can go a little bit awry. And then you'll explore it. You'll filter it down, do some munging, and then you'll throw it on a map. And you'll ask yourself for the first of many times, does something on this map look weird to me? Next, you'll join it and combine it with other data, whether it's spatial or non-spatial. Maybe you're going to overlay roadways or real estate sales, for example. Then you have the analysis step. This definitely takes many forms and can take a long time. But if you're doing something like creating a prediction model, you'll probably do at least some basic feature engineering. So say perhaps you're trying to predict home sale prices like Zillow does. One thing you might want to do is calculate and predict the average price of all recent home sales that occurred within a half mile of a given property. So something like that would be an example of spatial feature engineering. And then lastly, you'll move on to the findings. We'll take what we learned make some final takeaway maps, charts, and write-ups, and deliver them to your stakeholders. But every step of the way, we're asking ourselves, does something look weird? And this is definitely true in evaluating any data set. It's certainly not unique to spatial data. But one reason I think it's especially prominent in evaluating and working with spatial data is because visual oddities are very easy to spot, and it's really easy for anyone to spot them. You don't have to be an analyst who's super close to the data to know that the store footprint to a given, I don't know, Pizza Hut is wrong, but you might need to have more domain knowledge to know that the square footage number itself is wrong. Spatial data when spatial data is wrong, it's often very obviously wrong.
So Eugene, so I'm gonna have Alan was asking actually a question about that previous slide. I'm gonna allow Alan. I'm gonna unmute you, and if you want to ask Eugene your question.
Yeah. Hi there, Eugene. Yeah, thank you. You were talking through how you used Python, and then you talked about Spark, and you were talking about extensions on the Spark platform. We're in the Spark environment. We're looking at moving from a CodeBricks to a Spark environment, and I was curious as to A, your thoughts on that, and B, the geospatial extensions you're using on Spark.
So the one I've been working with in my day-to-day, I'm mostly querying the data rather than as opposed to like the engineers where I guess a little bit closer to like the data production process. But in my day-to-day, I like to use Apache Sedona as a sort of spatial extension to Spark. It's got like a Python and SQL API, so it's very familiar if you've used like PostGIS. It has a lot of the same syntax, so it's pretty easy to plug and play. I think one challenge with it is a little bit less mature, so some of the functionality isn't quite there yet, and you might need to write some like user-defined functions to make things work, and sometimes it can be a little buggy. So it's definitely something worth exploring, but I've had success so far with Apache Sedona.
Okay, perfect. Thank you very much.
No problem.
Thanks, Alan. We actually had one other individual, and I apologize if I butcher your name. Edith raised his hand. I'll allow you to talk as well if you have a question. Let's see. Well, if you might have been an errant hand raise, so if you do think of a question, please let me know. But for this time, I'll let you proceed, Eugene.
All right, so I want to wrap up with just a couple quick hits of spatial data terminology. When you enter the sort of spatial analysis world, you're going to run into a lot of terms, and it's going to be kind of overwhelming. But I think these are two that are worth focusing on because you'll see them in every analysis you do, and it's good to get it cleared out of the way. So the first is actually pretty simple. It's the spatial join. And the question we have here is, how do you join spatial data together? It can be very similar to doing a regular join when you're joining two tables together. You might use something like a census block group ID to join things together, similar to how you might take a data set of credit reports and a data set of incomes and join it together using people's social security numbers. So it could be the same thing as that. But you can also specifically do a spatial join, where you consider the geographic relationships of pieces of data to perform the join. So one approach might be to do a point and polygon. So on the right side, you might say, into which orange polygon does each of these green points fall? You can do that sort of approach to find which census block group your bodega is located in to draw some conclusions about the customer demographics, its customer demographics. But the function you use can be much more complex. You can do something like a nearest function or a within distance or a at least this distance from type function. So for instance, if you're looking at a Starbucks, you could choose to join it to the nearest Dunkin' Donuts, or you could choose to join it to all Dunkin' Donuts within 10 miles, etc. So that's a spatial join, which is using a data set's spatial attributes to join it with another data set. The other bits of terminology I want to touch on are coordinate reference systems and projections. And this is probably the most esoteric part of the chat, but I think it's among the more interesting, and you'll definitely encounter it in your GIS work. So I want to make sure to touch upon it here. When someone refers to a coordinate reference system, really they're saying, how do you use coordinates to express a position on Earth? When you hear latitude and longitude and degrees, you're using what's called a geographic coordinate reference system. Latitude and longitude are actually angles, hence degrees, from the Earth's center, as you can see in the picture in the bottom right there. Interestingly, not everyone uses the same, quote, model of the Earth. So a given latitude and longitude pair can mean slightly different places on the Earth, depending on the model you're using. One fun fact about this is that, so there's one commonly used model of the Earth, and it's referred to as WGS 84. And this was created to try to keep as many of a set of points around the globe in the same place as possible over time. Another model, NAD 83, was created in 1983, so just a year apart, to try to keep as many points in North America the same over time. So when they were both created in the early 80s, a lat-long pair, latitude-longitude pair in one of them meant basically the same thing it did in the other. But as those decades have passed, they've actually slowly drifted apart due to movement in the plate tectonics. And the plate tectonics move maybe a few centimeters every year. So now coordinates in those two systems can be up to a meter apart in real life. For most data, they're interchangeable because most people don't actually care about maybe like 1 meter of difference. But in some applications, like if you're doing land surveying or something like that, it's actually really important to keep the CRS in mind because you might be looking at latitude and longitude, but you might be off by a meter if you're not sure which model of the Earth it was based on. On the other hand, a projected CRS is a flat representation, a map of the Earth. Choosing a projection is much more complicated, and they're not as interchangeable as the geographic coordinate reference systems I talked about on the last slide. The issue is that inherently you cannot flatten the Earth into a rectangle without distortion. It would be like peeling an orange and trying to get a rectangle. It just can't happen. The units for a projected CRS are not degrees from the Earth's center, but rather they are XY distances from an origin, just like a Cartesian plot, like you might have drawn in like pre-algebra. That might be Null Island, which is that little buoy, which is at the intersection of the equator and the prime meridian, or it might really be any arbitrary point anywhere else on the globe. But the projection is critical to keep in mind because it not only affects how your spatial data looks on a map. So for instance, look in the bottom left corner and you could see that the shortest distance between New York and Moscow is actually that arc that cuts through close to Greenland and over Iceland, rather than the straight line on the flat map. So the projection not only affects how your spatial data looks on a map, but it also affects distance and area calculations. A common mistake beginners make is to use what's called the web Mercator projection, which is sort of like the standard web projection used in web maps on the internet, with the exception of Google Maps. And they end up using that projection to make calculations. And basically, the further you get from the equator, the more distorted calculations you make using that projection will get. So before doing some sort of distance calculation on projected data, you'll want to make sure to choose an appropriate projection for the area you're looking at.
So Eugene, we have another question from Michael. Michael, I'm going to allow you to talk. Give me 1 second so you can ask your question. All right, go ahead.
Sure. My question is, I'm presuming that these coordinate reference systems that you identified are what would be categorized as open geospatial data. My question is, are there similar governmental or international standards efforts underway to ensure that AR point clouds, as they emerge, also remain open?
What are AR point clouds?
So these are the geospatial coordinate maps that are used for augmented virtual reality.
Oh, interesting. Yeah.
Yeah, they define 3D space above, our spheric geospatial data.
Right. Yeah. That's very interesting. Yeah. As you might be able to tell, I'm not familiar with that, so I don't have an answer to your question. But it's something I haven't really thought about, like the standardization of like the 3D projection space.
Yeah, it's a major issue for the future, as you can imagine.
How do companies that do like VR type simulations and things, how do they solve that problem right now? Do they all have their internal systems, or do they?
Yeah, I mean, there is the Open Geospatial Consortium wading into this, the Open AR Cloud Association, but what we're seeing right now is, the future on the spatial web is being carved up into digital feudal kingdoms.
I
And
see.
you can imagine that if the map of the world was carved up the same way, which we've seen over the centuries, the implications don't bode well for the future.
Yeah. Well, I'm sorry I don't have an answer for you, but thanks very much for asking that. It's really interesting to think about. All right, so that actually concludes my presentation. So I did want to leave you with a few references and readings. Again, this is definitely geared towards a beginning audience, but for those who are interested in sort of diving into the space, I do have 2 recommendations on people you can follow. So the first is Joe Morrison. He is a newsletter writer and prominent Twitter user, tweeter. He's very online. And he writes with an Earth observation satellite imagery focus, but he's just a great follow for knowing about the geospatial industry, as well as the Mapscaping podcast, which is essentially interviews with any and all sort of spatial analysis people and companies at all levels. And then for some deeper dives, both for like terminology explanations, but also for some applied work and applied skills practice, you could reference any of these. And I'll make sure to share at least this slide with the group after today's talk. With that, I'll take it to any questions and leave the screen on my favorite map that I've seen in the past couple of years.
Awesome. Well, thank you so much, Eugene. We did have a request if we would be able to post a viewable link to the presentation in the chat for someone that would love to dig into those readings later. We'd certainly be able to do that. A couple of final things. I'll give everyone a few more minutes in case there's any lingering questions. But just looking ahead, just another reminder, we do have that fireside chat coming up next week, next Friday. Information can be found in the chat. Also, just looking ahead, so like I mentioned, since this is our first event kind of in this knowledge series, just to give you a sneak peek as far as some of the other topics coming up in the future. We will have a couple other ones in the coming months, working with large data sets and working with time series data. So keep your eyes peeled for those. We will certainly get you information and we'd love to have you all back, but I'm not seeing any other questions, just to double check. Yeah, I will, at that point, then I will go ahead and wrap things up. Thank you again so much, everyone, for attending. Have a great rest of the weekend, and we will talk to you all soon.
Thank you, everyone.
Yeah, take care.